we have here another example. We have y multiplied by 2xy plus 1 dx minus x dy is equal to 0. Okay, so as you've noticed, we cannot see directly where is our exact differential here, and maybe we need to do some algebra first. Say we need to multiply this 2xy squared dx. Let me multiply this also. So y dx multiplied by 2y dx is 2xy squared dx plus y dx, right? We have y dx. Then minus x dy is equal to 0. Okay. So based from this given differential equation now, how can we, or did you see, or I mean, do you see any exact differentials here? Did you see already? Or do you have something in mind that can modify this equation for us to have the exact differential? Okay, so let me go back first here in our last example. So based from here equation, we can directly see our exact differential, which is this part, the the derivative of x and y, because that is already the derivative of x and y. Okay, but in this part, we cannot identify directly where is our exact differential here. But as you've noticed, we have here this part, the y dx minus x dy. And if you think of or if we observe that we can have a an exact differential if we divide this by y squared. Why? Because remember this y dx minus x dy, because if we've multiplied that by y squared, we can now have this part here, the exact differential, which is x over y. Okay, so that is equal to y dx minus x dy all over y squared. That's why you need to exercise your mind and practice more of this kind of technique. Okay, so say if we divide our both sides by 1 over y squared, so this is now our integrating factor, because if we multiply this, we can make a expression that is an exact differential. Okay, so if we multiply this, what we have is can cancel this out, so we have 2x dx plus y dx minus x dy all over y squared, right? And as we say that this is equal to the exact differential the x over y, right? Because this is low times derivative of the high minus high times derivative of the low all over low y squared, y times y. Okay, so it's 2x dx. Okay, so all in all, we can express our differential equation in this form. Okay, and then by also by analyzing our equation, we can say that this both terms are now integrable. So we can now proceed to integration. We have 2x dx plus the integral of dx over y is equal to 0. Integral of 0. Okay, by doing that, we have 2x squared all over 2 plus the integral of this derivative, we have x over y is equal to c. So this is now our general solution. Okay, once again, based from our initial given dE, say this is our equation 1, and then we think some modifications in order for us to find some exact differentials, and we notice that we have y dx minus x dy, and by thinking, we think that if somehow we've divide this whole term by y squared, we can now have this exact differential. So we do that. Okay, so we by inspection, we say that we need to divide this whole term by y squared. So that is the integrating factor that we need. Okay, so by doing that, we've come up with this exact differential, the derivative of the x over y, and then we have the 2x dx. And fortunately, by doing that, we are now have terms that are both integrable. So 2x dx, we have a purely function of x alone, 2x dx, so that is integrable, and by integrating, we've come up with this. So by the way, we can cancel this out, and then this term here is also integrable. Okay, so we have the integral of this derivative is the x over y, and then our plus c. Okay, so that is the technique of using the integrating factor by only inspection. Okay, so I hope you've learned something again from this, and see you next time again on our next video for more samples.